Yo, welcome to Physics with Vinay. In this lecture, we're going to cover laws of motion. So, Newton's law states that the net force on a system is rate of change of momentum. For a single object or a point particle, if I have mass m and its velocity vector is v, so clearly the net force would be dp by dt, which would be equal to ma vector. So this is the equation that is the basis of this entire chapter. And very important, Newton's third law, that action and reaction are equal in magnitude and opposite in direction. So basically internal forces cancel out. So on a system, the net force is ultimately only the external force, the summation of all the external forces. Newton's laws are valid only in what we call inertial frames. So inertial frames are defined as those frames of reference in which Newton's laws are valid. Now in a non-inertial frame, what is a non-inertial frame? It is a frame that is accelerating with respect to an inertial frame. So it has been established that ground frame, the frame of Earth, is approximately inertial. Now why am I saying approximately inertial? Because it is actually rotating, and because it is rotating, it has some acceleration. It's rotating as well as revolving around the sun. So it does have some acceleration, but the acceleration is small enough that we can treat it as approximately an inertial frame. So that is what we're going to do in this chapter. And any frame that is accelerating with respect to ground frame will be a non-inertial frame. So in this chapter, any frame that is accelerating with respect to ground frame. So in the non-inertial frame, what we do is, in addition to the real forces, we add a pseudo force. So pseudo force is an imaginary force that we need to include in our free body diagram if we want Newton's laws to be still valid, in the sense that the net force should be equal to ma. So that net force should have an extra term of the pseudo force. So mathematically, what is pseudo force? Pseudo force is given by mass of object times the acceleration of the frame of reference in which you are observing the motion of the object. So acceleration of the non-inertial frame. And the direction, so let me just put a vector sign here, and there should be a negative sign here. So the pseudo force vector acts opposite to the acceleration of the frame of reference. So you just have to include this pseudo force in addition to the rest of the real forces in your FBD, and then you can proceed as usual when you're solving or when you're writing the force equation or when you're trying to apply Newton's laws of motion. Alright, now let's look at the concept of normal force. So if I have an object placed on a surface, so the surface is going to apply a force on the object. That force may have two components. One is perpendicular to the surface and one is along the surface. So the component of the force by the surface on the object perpendicular to the surface is called the normal force. The word normal itself denotes that it is perpendicular to the surface. And the component of the force along the surface is called friction. So we'll deal with friction later on. For now, we are going to deal with smooth surfaces where friction is absent. So the normal force is always perpendicular to the common surface between the two objects or the object and the surface, and it is a pushing force. So the surface will push the object upwards and the object will push the surface downwards. So it's always a pushing force. Now sometimes you get the situation where a surface is not well defined. By that I mean, suppose I have, let's say, a cone on the ground. So at the apex of the cone, the surface has a sharp corner. So in such cases, normal force, the direction of the normal force is perpendicular to the defined surface, the surface that is well defined. So by that, in this example, by that I mean that the ground, the red surface is well defined, so the normal force will be perpendicular to it. The reason is that in reality, there is no such thing as a sharp corner. In reality, this cone will actually have a smooth, there will be a smooth curve at the apex that we don't bother about in our questions. So the common surface will basically be the tangent. and therefore the normal force will be perpendicular to the common surface between the cone and the red surface. Another example, if I have something of this sort. So I have a cuboid resting on two inclined planes. So once again, the direction of the normal force will be perpendicular to the defined surface, or perpendicular to the inclined plane. So these red arrows will be the direction of the normal forces. So I hope you've understood how we can identify the direction of normal force. Now, one very important concept is, suppose I have a person standing, let's say on a weighing machine. Let's say the person has a mass of 72 kg. So if I draw the FPD of this person, the person has a gravitational force acting on him of mg. So let me take g as 10 meter per second squared. So that will be 720 newtons. Now, a very important concept to understand is that this force, what is this force? This is the gravitational force by Earth on the person. It does not require any contact. This is not the force applied by the person on the weighing machine. That is very important to understand. Mathematically, they may be equal, they may not be equal in different cases, but this is not the force applied by the person on the weighing machine. So the normal force in this particular situation will cancel out the gravitational force and will be equal to 720 newtons mathematically. And the reason I have given the case that the person is standing on the weighing machine is because the weighing machine reading is the normal force. The normal force that the person applies on the weighing machine, or what the weighing machine applies on the person. It will be the same in magnitude by Newton's third law. So the reading is not the weight of the person, it is the normal force. So that is important because if, suppose I take the case where, suppose on this person, iske takle pe suppose I apply a 20 Newton force. So what will be the normal force? Earth is applying a gravitational force of 720 Newtons, and therefore the normal force will have to be 740 Newtons. So the reading of the weighing machine will not be 720, it will be 740 Newtons, and usually they are calibrated to give the reading in kilograms. So it's normal force divided by G. So the reading in this situation would be 74 kg. So the reading of the weighing machine is not the weight, it is the normal force. If I ask you what is the force by the person on the weighing machine, is it the weight of the person? No. That is the usual misconception that students have. It is not the weight of the person, it is the force that the person is applying through his feet on the weighing machine, which is the normal force. So that will be 740 Newtons. And similarly, agar iske takle pe I pull two hair with, let's say, 20 Newton. I pull his hair with 20 Newton force. Then what will be the normal force? What will be the reading? His weight is 720. So clearly the normal force will be 700 Newtons for equilibrium of the person, and therefore the reading would be 70 kg. And the force by the person on the weighing machine, like the previous example, will be 700 Newtons, not 720, it will be 700 Newtons. So I hope you've understood the concept of normal force and the concept of the force applied by a person. You have to remember that in our chapter in mechanics, gravity is the only force that acts without contact. Gravity is the only force that does not need contact for acting. Every other force in mechanics, normal force, tension force, all these forces require contact. So when you draw the FPD of an object, it's very easy to draw the forces because one force will be gravity, and all the other forces you just have to check what the object is in contact with. So let's do a question. Three identical cylinders are arranged in a triangle as shown with the bottom two lying on the ground. So these are three cylinders. The ground and the cylinders are frictionless, and you apply a force directed to the right on the left cylinder. What is the minimum and maximum acceleration you may give to the system in order for all three cylinders to remain in contact with each other? So I have three cylinders in this manner, and I'm applying a force such that they all should remain in contact with each other. So just imagine that if you have zero force, if you just leave this system and apply zero force, the top cylinder will simply tend to fall down and the bottom cylinders will separate out. So the minimum acceleration that we need to give is to ensure that the bottom cylinders are in contact. So we are going to set the normal force between the bottom two cylinders to just 0. Now if I draw the FPD of the cylinders, so let me just first label them. So if I draw the FPD of cylinder C, on cylinder C there will be a normal force by A, let's call it N1. Now you should be able to see that the lines joining the centers will form an equilateral triangle because they are all identical cylinders. So therefore this angle will be 60 degree, and therefore can I write N1 cos 60 will provide the horizontal acceleration for C, so that will be equal to ma. So this is one equation. Basically this tells me that N1 value is 2ma. So this is one equation that we've gotten. Alright, now if I draw the FBD of A, so I have the normal force N1 whose value is 2ma. Let's say that the cylinder B is applying a normal force of N2. So they'll have to balance the weight of A. So can I write N2 cos 30 in the vertical direction plus N1 cos 30 should be equal to mg. So just by substituting N1 as 2ma, I will get N2 as 2mg by root 3 minus 2ma. Now if I draw the FPD of A in the horizontal direction, so for A in the horizontal direction, we'll have components of N2 and N1. So I'll have N2 sin 30 minus N1 sin 30 to the right should be equal to ma. Now all I have to do is substitute N1 and N2 here, and you solve for A. So you will get A as g by 3 root 3. So I'll leave the calculation up to you, and this is the minimum acceleration that is required such that B and C do not lose contact. Now let's look at the maximum acceleration that can be provided. So let's do that on the next page. So if you want, you can pause the video and you can try out the maximum acceleration required, follow a similar process here, but now you have to figure out where the contact can be lost when the acceleration is at its maximum. So just try it out and then you can take a look at my solution. So in this situation, it will be helpful to go in the frame of the system in order to visualize what is happening. So for maximum acceleration, let me go in the frame of the system of cylinders. So all the cylinders are accelerating to the right with A, and therefore they will have pseudo forces this way, opposite to the acceleration of the frame of reference. Therefore there's an external force here F. So now you should be able to see that as we increase the acceleration, the contact loss is likely to happen between A and C, because A only has this external pseudo force in the horizontal direction, which is likely to pull it away from C. For maximum acceleration, we're going to set the contact between A and C to be 0. So normal force between A and C, which I labeled as N1, I'll set that to 0. Now if I draw the FBD of A, so I'm going to continue working in the frame of the system. So obviously all the cylinders will be in equilibrium. So on A, I'll have a pseudo force ma and the normal force N2 and of course mg. So now I can just balance forces. I'll have N2 cos 60 should be equal to ma, horizontal direction, and N2 sin 60 should be equal to mg. So I immediately get acceleration as g by root 3. That will be a maximum acceleration. Now let's look at inclined plane. So if I have an object on inclined plane, the components of gravity are mg sin theta, mg cos theta. So the normal force will cancel out mg cos theta if the inclined plane is stationary, and the acceleration of the block would be g sin theta, because the only force that will be acting on it will be mg sin theta. Now if the inclined plane is also moving, so basically if I have, suppose, this sort of a situation. So inclined plane is also free to move and the block is also sliding. So in such situations, we have a constraint equation for the block and the wedge to remain in contact. So what we are doing is what we're calling constraint equations or wedge constraints. The wedge constraint states that the displacement of the blocks along this normal axis, so this is the common normal between the block and the wedge, the displacement component of the block 1 along the normal axis should be equal to the normal component of the displacement of the wedge. So whenever you have two surfaces that are supposed to be in contact, they should have obviously the same displacement along the normal, or else either they'll lose contact or they'll break. So this is a constraint, and if you differentiate this, you'll also have the same relation between velocities, that the component of velocities along the normal should be same, and similarly for acceleration. So for example, if I have this wedge and I have another wedge in this manner, this is acceleration a1, and let's say this is a2, and let's say this angle is theta. So I want to find a relation between a1, a2 and theta, just a constraint relation. So the best way to do this is just draw the horizontal and vertical and draw the common normal and the common surface. So horizontal and vertical, and the common surface is this green surface, and this is the common normal. So the common surface is triangle theta. This is my common normal. So I have a2 and a1, and now it's very simple. The components of a1 and a2 along the normal should just be equal. So I'll have a1 cos theta should be equal to a2 sin theta. So that's a kinematic relation between the accelerations. Now suppose you want to find the actual acceleration if you're given the masses. We'll have to use Newton's laws as well. So let's do that on the next page. So I'll continue the same example that we just did. I have this sort of a wedge, and then another wedge here. So let's say masses are m1 and m2, and this angle is theta. So we already found a relation between a1 and a2. So we had a1 cos theta should be equal to a2 sin theta. So this is the constraint equation. And now what I'll do is I'll express a1 and a2 in terms of the common normal force between the two. So on the top wedge, on m1, I'll have the normal force this way. This angle is theta. So can I write that a1 should be equal to m1g minus the vertical component of normal force n cos theta divided by m1. So I'm just substituting it directly in a1. So this is just the way to do it in the exam. Always write the constraint equation first. So that makes it very easy, and then express all the accelerations in terms of the normal force. And what about a2? For a2, I have a normal force this way. This angle is theta. So normal force is the only force that has a horizontal component on m2. So I can write that as n sin theta, horizontal component of n, divided by m2 times sin theta. So just solve for n. So basically we kind of avoided simultaneous equations. So just solve for n, and once you have normal force, this expression will be a2, and once you have a2, use the constraint to get a1. So I hope you've understood the process for this type of question. Let's do one more question as a practice problem for you. So I have two wedges, and wedge A will slide along this incline, pushing wedge B to the right, pushing block B to the right, and find the acceleration of A and B. Both have the same mass as m. So pause the video, try it out, and then check if you've gotten the correct answer. Alright, so first thing, like I said, we'll write the constraint equation. So acceleration of A is in this manner, and acceleration of B is to the right. So the common surface is the vertical. So the vertical itself is the common surface, so the horizontal is the common normal between A and B. And acceleration of A is at 45 degrees, and acceleration of B is along the normal itself. So component of acceleration of A along the normal, A cos 45, so should be equal to the entire acceleration of B, because it is entirely along the normal. So this is my constraint equation. Now I'm going to substitute the accelerations in terms of the normal force. So for A, the normal force is this way, and I'll have a component of gravity which is mg sin 45 along the incline. So along the incline, the acceleration of A, can I write it as mg by root 2, and the component of normal along the incline will also be n cos 45, so n by root 2 divided by m. This is the acceleration of A divided by root 2 should be equal to acceleration of B, and acceleration of B is very straightforward. It only has a normal force acting on it completely along the horizontal, so n by m. So now all I have to do is solve for n. So I will get n as mg by 3. And once you have n, acceleration of b will simply be n by m, so g by 3, and acceleration of a by constraint equation will be root 2 times acceleration of b, so root 2 g by 3. So I hope you've understood how to solve such wedge problems. Now let's take a look at a nice question. The wedge shown can slide without friction on a horizontal floor. Mass of the wedge is capital M and its inclination angle is 30 degrees. A block of mass M slides on the wedge without friction. So this block is able to slide down when released on its inclined phase. If the path of the block relative to the ground is along this dotted line, makes an angle of 60 degrees with the horizontal, find the ratio of the mass of the block to that of the wedge. Alright, so if you want, you can pause the video and give it a try. This is a nice question, and then you can take a look at my solution. Alright, so acceleration of capital M, let me call that A1. So let's say the wedge is traveling to the right with A1, and the acceleration of small block, let's say A2. The small block is at 60 degrees in this manner. So the relative acceleration is along the incline. So A relative is A2 vector minus A1 vector. So A2 vector minus A1 vector, if you notice, this is A2 vector, this will be minus A1 vector, and the resultant will be A relative. So you should be able to see that this is 30 degrees, this is 60 degrees, so this angle will also be 30 degrees, and therefore A relative is bisecting the angle between A1 vector and A2 vector, and therefore the magnitude of A1 and magnitude of A2 are equal. You could have seen this from triangle law also. You could have drawn a triangle between A1, A2 and A relative, and you would have gotten an isosceles triangle with the equal sides as A1 and A2. Anyway, now that we have that the magnitude of acceleration of the block in the ground frame and the wedge in the ground frame are equal, now what I'm going to do is I'm going to say that there is no net horizontal force on the system. The net horizontal component of the force is 0, and therefore I can write mass of the wedge into A1 minus the block has a component of A2 cos 60 in the horizontal direction. That is a component of acceleration, but it's in the left direction. So the net force on the system, I can write it as M1A1 plus M2A2 plus M3A3 and so on. So this is for the wedge, and for the block I'll have minus MA2 cos 60. Now because A1 and A2 are equal and this entire system has no horizontal component of force, so I'm going to equate that to 0, and A1 and A2 will cancel out, and I'll simply get M by capital M as 2. So I hope you've understood how to solve this question. Now let's look at string constraints. So whenever you have a pulleys and strings involved, so the string constraint is basically that the length of the string is a constant. Suppose I just label the blocks as 1, 2 and 3, and let's say all of them have a displacement of S1, S2 and S3. Now obviously one of these quantities S1, S2, S3 has to be negative because one of the blocks will at least be going upwards, otherwise the string will break. The total length of the string has to be constant. So what I'm going to do is I'm going to write the total length of the string as constant. So the change in the length is 0. So this red segment is increasing by S1. These blue segments are increasing by S2 each. So I'll have plus 2 S2. And finally this green segment is increasing by S3. So this should be 0. And if I just differentiate it once, I'll get, and once more I'll get the relation between the accelerations. So obviously not all these quantities can be positive, but it doesn't matter. The final equation or the final answer will tell us which one is negative, so we don't have to worry about figuring out at the beginning which block is going up or which block is going down. Now when you have multiple strings involved, then it is easier to use the concept of virtual work method. So virtual work method basically just is that the work done by the tension is 0. So the net work done by tension is 0. So if I have a tension T acting on block 1, I'll have tension 2T acting on block 2 because the pulleys are massless here. So the net force on the pulley should be 0. So if I have an upward T and T on the pulley, moving pulley, I should have 2T downwards on the moving pulley, so 2T on block 2 and T on block 3. So these are the tensions on 1, 2 and 3, and therefore the work done on block 1 would be minus TS1, work done on block 2 would be minus 2TS2, and work done on block 3 would be minus TS3. The negative sign is because the tension and the displacement are in opposite directions. So I'll get the same relation that we got earlier here. the work should be 0. So this is the virtual work method. It's very useful when you have multiple strings, so you don't have to write multiple equations for each string. You can just write one straight equation relating the accelerations and the displacements of the blocks. And if you have strings at an angle, so for example, suppose I have this sort of situation where block 1 is traveling with velocity v1 along the horizontal, block 2 is also traveling along the horizontal with velocity v2. At a particular instant, this angle is theta. So the total length of the string should be a constant. So if I look at this red segment, the red segment is decreasing at a rate of v1 cos theta, component of v1 along the red string. So rate of change of red length is minus v1 cos theta, and the rate of change of this blue length is increasing at the rate of v2 itself. So plus v2 should be 0. So I'll have v1 cos theta is v2. This is what we actually saw in kinematics as well, in the second lecture of kinematics, where we calculated the rate of change of lengths, and that is the same principle we are using here. So let's do a question. 3 blocks A, B and C are suspended with the help of 3 pulleys and 2 threads with equal horizontal separation. So we have equal horizontal separation between AB and BC. Initially the blocks are held at rest at the same level, the same horizontal level, and then released. The blocks move in such a way that they always remain in a straight line. And if at an instant the block B is observed moving downwards with velocity 4 cm per second relative to block A. Relative to block A, that is the important point. Find the velocities of all the blocks at that instant. So let's say A is traveling upwards with velocity V, and it may be traveling downward also. If V comes out to be negative, then it will be traveling downward. We can just assume it in any direction. So because B is moving downward with 4 cm per second relative to block A, so the ground frame velocity of B would be 4 minus V. This is just a relative equation. And let's say velocity of C is Vc. So if I just label the tension T, this will also be T, and therefore this will be 2T. I can write the virtual work method. So on block A, the work done would be 2T into displacement. If I differentiate, displacement will be replaced by velocity. So I'm just going to write it directly. So 2T into velocity for block A, same direction, so there's a positive sign. For block B, T and 4 minus V are in opposite direction. So minus T times 4 minus V. And for block C, also in opposite direction, should be 0. So this is the virtual work method, and therefore Vc would be equal to. Alright, so I've gotten everything in terms of V, all the velocities in the ground frame. Now what they're saying is find the velocities of all blocks. So therefore I need to find the value of V. Now the question says that they move in such a way so that they always remain in a straight line. So I have A, B and C. So at some instant A will go up, B will go down, C will also go down, and they will all remain a straight line. So C will end up here. Now in order to solve this question, it will be easier to go in the frame of one particle because there are 3 particles moving. So let's go in the frame of one of the particles, let's say in the frame of A. So then A will be at rest, and then we only have to worry about the motion of 2 particles. So in the frame of A is at rest. B will have a velocity of 4 cm per second downwards as given in the question. So in time t it will travel a distance of how much? 4t. And C, what will be the velocity of C with respect to A? So velocity of C with respect to A in the downward direction would be 3v minus 4 minus of minus V, because A has a velocity V upwards. So that will be 4v minus 4 in the downward direction. So in time t it will travel a distance of 4v minus 4 times t. Now because AB is equal to BC given to us in the question, so you should be able to see from similar triangles or even from trigonometry that this 4t should be half of this quantity. So 4t should be half of the displacement of C. This is with respect to A. So therefore I'll get V as 3 cm per second, and that is the velocity of A. And once you have the velocity of A, velocity of B is 4 minus V. So velocity of B would be 1 cm per second, and velocity of C is 3v minus 4. So velocity of C would be 5 cm per second. So that's your answer. Alright, let's look at another type of problem. Okay, so here I have 2 blocks connected by a string going over a pulley, and that pulley itself is moving with horizontal velocity Vp. The blocks are moving with V1 and V2, and the angles at this particular instant are given theta 1, theta 2. And the red diagram here, the red circle here is a motor around which the string is getting wound. So the string is wrapping around the motor. The question is asking us the relation between V1, V2 and Vp. So in order to solve this type of question, what we're going to do is we're going to write down the rate of change of individual segments of the string. So suppose I look at this blue segment connected to block 1 and the pulley. So the top point of the blue segment is traveling with Vp, the lower point of the blue segment is traveling with V1. So what is the rate of change of length of this blue segment? So can I write dl1 by dt should be equal to, this angle is theta1, this angle is also theta1. So this will be Vp cos theta1, that is the component of Vp along the blue line, and I'll have a minus V1 cos theta1 because V1 component of along the blue length is going to try and decrease the blue length. Similarly, can you do the same for this green length? Let's call that L2. So for the green length, the lower point has a velocity V2 and the upper point has a velocity Vp, and these angles are theta2. So I can write dl2 by dt. It's increasing due to V2 and it's decreasing due to Vp. And finally, what about the length around the motor? So the length around the motor, let's call that L3. So the length around the motor is increasing at a rate of, so let's say motor wraps the length at a rate of V4. So the dl3 by dt would be equal to V4. Basically the red length on the motor is increasing by V4. Alright, so all we have to do is that the sum of the rate of change of lengths should be 0. So I'll simply have dl1 by dt plus dl2 by dt plus dl3 by dt should be 0. So the summation of these three quantities should be 0. So that's your constraint equation. Now a very important point to note here is, suppose I have a simple situation in this of this sort. So now it should be very straightforward to write the constraint equation that this blue length will decrease at V1 cos theta1 and this green length will increase at V2 cos theta2 should be 0. The total rate of change of length should be 0. So V1 cos theta1 should be equal to V2 cos theta2. Can I write A1 cos theta1 by differentiating is equal to A2 cos theta2? So this is wrong because when I differentiate this equation, I'll have A1 cos theta1, I'm differentiating V1, but theta is also changing. So I'll have to use product rule. So I'll have minus V1 sin theta1 d theta1 by dt. And similarly on the right hand side, I'll have derivative of V2 A2 minus V2 sin theta2 d theta2 by dt. I've just differentiated cos theta1 and cos theta2 with respect to time. So this will be the relation between accelerations. There is one condition in which A1 cos theta1 will be equal to A2 cos theta2, and that is when the objects are at rest. So often in such type of questions, they'll release the system from rest and they'll ask you the initial accelerations. So in that particular case, at that particular instant, this relation is valid. So I hope you understood how and when we can apply the relation between accelerations. Now let's do a pulley problem. So in this question, I have all pulleys as smooth and all the strings are massless. The question is asking us to find the acceleration of the pulley A and pulley B. So they have both the same mass, and because the pulleys are smooth, there is no friction acting on the pulley, so there is no worry about the rotation of pulley. We are not concerned with the rotation of the pulleys. Alright, so you can pause the video and give it a try, and then you can take a look at my solution. Alright, so first let's write the constraint equation. So let's say that the tension in the string is T. So you should be able to see that there is only one string here. There's only one string going around. So in a single string, the tension everywhere will be T. So I have T, T. So on A, so let's say A is going upwards, the acceleration AA, and let's say B is coming down with acceleration AB. So what is the net tension on A? 2T. And what's the net tension on B? T in the upward direction. So therefore, when I write down the virtual work method, so I can write on A 2T into displacement of A, but when I double differentiate, I'll get acceleration. So I'm just going to directly write acceleration of A. And for B, there is a resultant tension of T upwards and acceleration is downwards. So I'll have a negative sign because the force and the acceleration are in opposite direction. So minus T times AB should be 0. So therefore, I have AB is 2AA. This is the constraint equation. Alright, now I'm going to write the force equation. So on B, the forces are T, 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 resultant of T upwards and mg downwards. So can I write acceleration of B as mg minus T divided by m should be equal to twice of acceleration of A. And what is acceleration of A? For A, I have 2T upwards and mg downwards, and we've assumed A to be moving upwards, so that will be 2T minus mg divided by m. Alright, so just solve for tension and you should get tension as 3 mg by 5. And once you have tension, now it's very straightforward. Acceleration of B would be mg minus t by m. So that will be 2g by 5. And acceleration of A, just using constraint equation, it will be half of acceleration of B. So acceleration of A would be g by 5. Alright, so those are the answers that you should have also gotten. And if not, I hope you've understood the solution. Let's do one more problem. Alright, so in this problem, all pulleys are massless. And smooth. The question is asking find the acceleration of A and B. So give it a try and then you can have a look at the solution. Alright, so this is a slightly different problem where virtual work method is not useful. It fails to give us any new information, and the reason is that suppose I try to write virtual work method here. So let's say this tension is T, this will also be T, this will be 2T, T. And can you see that this is a single string here? And therefore the tension here should also be T. But this leads to a very unusual situation where this green pulley is massless. So on a massless pulley, that means mass is 0, net force should be Ma, that means net force should be 0. However, you can see we have an unbalanced force of T downwards on the green pulley, but that simply means the tension itself has to be 0. Because this is massless, the net force on it has to be 0 using Newton's law, F is equal to Ma. And therefore T itself has to be 0. And if T is 0, then virtual work method is not valid, or rather virtual work method is useless. The reason is because if T is 0, then for any displacement for A and B, the net work done by tension will be 0 because tension itself is 0. So we will not get any new information, it will be an identity. So for example, when I showed virtual work method here, if tension here is 0, then we cannot cancel tension out. So that's why we will never get this sort of a relation. When tension is 0, this is an identity because LHS is anyway 0. So we will not be able to cancel tension out here. When we divided by tension in this equation in order to get this next equation, the final result, we assume that tension is not 0. So let me just actually write that down. This is assuming that tension is not 0. So always be careful. If ever you have a situation where tension is 0, do not use virtual work method. You will get incorrect answers. Okay, so how do we go about doing this? So it's very straightforward now. Because tension is 0, on block A there's only gravity acting, so acceleration of A is g downwards. And acceleration of B is also g downwards because once again tension is 0. So acceleration of A and B are both g downwards. Suppose you were asked to find the acceleration of this green pulley. Then what you would have done is you would have written constraint equations without using virtual work method. You would have had to write the rate of change of length and equate it to 0 for the string. So let's say velocity of A is VA downwards, velocity of B is VB downwards, and let's say velocity of the green pulley is VP upwards. So let's write the constraint equation. Let's try and find a relation between VA, VB and VP. This blue length is increasing at a rate of VA plus VP. Then this red length is increasing at a rate of VP plus VB. What about this long red length? That is only increasing at a rate of VB. And finally, what about this yellow length? That is decreasing at a rate of VP. This should be 0. We'll have VP plus VA plus 2VB is 0. And therefore acceleration of pulley plus acceleration of A plus 2AB is 0. And I already know acceleration of A and B are G. So acceleration of pulley would be minus 3G. So the negative sign just denotes its opposite to the direction in which we assume. We assume the pulley to be going up. So the acceleration of pulley will actually be 3G in the downward direction. Now let's do a question where strings are at an angle. Suppose I have this situation. Let's say masses M1 and M2. And let's say a force F is acting and everything is smooth. The pulley is massless. The question is asking us to find the accelerations A1 and A2. At the instant it starts from rest. The system starts from rest. Alright, so the constraint equation, suppose I have velocity V1 and V2. This red length will decrease at a rate of V1 cos theta 1. And this blue length will increase at a rate of V2. So the decrease of the red length will be equal to the increase of the blue length, should be equal to V2. So this will be my constraint equation, and if I differentiate this, now we already saw this, that if I differentiate it, I should actually differentiate the angle as well, but because it is at the initial instant where the system starts from rest, at that initial instant we can actually write this sort of a relation for the acceleration. So the derivative on the right hand side would simply be A2. So this is my constraint equation, and then we can substitute A1. So what is the force acting on the block M1? You have a tension T. So A1 can simply be written as T cos theta 1 divided by M1. This is the horizontal component of tension times cos theta 1. And what about A2? A2 has a tension force acting to the left and external force F. So F minus T divided by M2. So from this equation you will get tension T, and once you have tension T, A2 will simply be F minus T by M2, and you can get A1 as simply A2 by cos theta. So this is how you will get A1 and A2. If you want to save a minute or two in the exam, there is a way to do this question in a single equation without solving simultaneous equations. The cute method here is to realize that we saw the constraint equation, that if the lower block has an acceleration A, this block has an acceleration A cos theta. The external force acting is F here. Now if I just open this string and make it into a straight line, so I've basically rotated this block along with the forces. So now the force is acting this way, and the acceleration of the block is A cos theta, and this acceleration is A. So now what I'm going to do is I'm going to write the net force in the x direction. So the net force in the x direction is going to be F cos theta. So for the lower block, I'm going to write net forces M1A1 plus M2A2 and so on. So for the lower block, it will be M1A, and for the upper block is going to be M2. A cos theta is the net force on it, but it's in this direction. So the horizontal component would be cos theta. And thus you can get the acceleration A. So this is a cute method, but I would suggest that pick the method that you're comfortable with, because the standard method here is also pretty quick. It's not too much effort to solve using the standard method. So pick whatever method you're comfortable with in the exam. So let's do another question. Alright, so the question is asking us to find the acceleration of all the blocks. So I have 4 blocks, A, B and C have the same mass m, and D has 2m. So you can pause the video and give it a try. Okay, so let's first assign variables. So let's say that the block A is traveling to the right with AA. You should be able to see that block B is in contact with A, so B will also have an acceleration of AA in the horizontal direction, and let's say ABY in the downward direction. Now let's say D moves to the left with acceleration AD, so C will obviously also move to the left with acceleration AD and also move, let's say, downwards. It is possible that between B and C, one moves up and one moves down. We don't know that. The final sign will tell us. So C moves down with acceleration, let's say CY. So these are the component accelerations of all the blocks. So now first let's write a constraint equation. So I have 3 segments to the string. This green length, this blue length, and this red length. So the green length is increasing at a rate of ABY. I should actually say the double derivative of the length is ABY. Similarly, the blue length. So blue length, A and D are coming close to each other. So the blue length is decreasing at a rate of AA plus AD. And what about the red length? The red length is increasing at ACY. So this should be 0 because the total change of length should be 0. So this is the constraint equation. Now it's very straightforward. So let's say the tension is T. So on block B, what are the forces? T and mg. So the equation will be mg minus T by m. This is the y component of acceleration of B. What about acceleration of A? So when I consider acceleration of A, I can consider A and B as one single system in the horizontal direction because they have the same acceleration in the horizontal direction. So can I say acceleration of A will simply be tension, the external force, divided by the total mass? So tension divided by 2m. What about acceleration of D? Similarly, D and C can be treated as the same system as far as horizontal motion is concerned. The acceleration of D will be tension divided by the total mass, which is 3m now. And what about the vertical component of acceleration of C? I have mg downwards and T upwards. So this will once again be mg minus T by m, and this should be 0. So now it's very straightforward. You can calculate T, which comes out to be 12 mg by 17. So I'll leave the calculation up to you. So now that you have tension, it's very straightforward to calculate the acceleration. So acceleration of A is t by 2m. So 6 g by 17. Acceleration of d is t by 3m. So 4g by 17. Acceleration of b will have a horizontal component same as a, and the vertical component will be mg minus t by m. That will be 5g by 17, and similarly for the y component of acceleration of c. So these are your answers. So even though the question looks very complicated, if you follow the process of first writing down the constraint equation and then substituting the accelerations in terms of the tension, it's actually very straightforward. We didn't have to solve any sort of simultaneous equation here, and the question was very straightforward once you follow the method. Let's do another string wedge problem. So I have 3 masses, MA, MB, MC are in the ratio of 1, 2, and 4, and find the acceleration of the wedge C. So let's say acceleration of C is A to the right, and let's say B is traveling with an acceleration of A relative to in the downward direction. This is relative to the wedge C, and therefore A will travel to the left. The same A relative again with respect to wedge C. So I'm going to write 2 equations to solve these 2 unknowns. One equation is that the net force on the system in the horizontal direction is 0. There is no external friction or any sort of horizontal external force on the system. So I can write the net horizontal force is 0. And my net horizontal force, I can write it as equal to m1a1 plus m2a2 plus m3a3. So for C, let's say the masses of A are m, 2m and 4m. So for C, I'll have 4ma. What is the acceleration of A in the ground frame? A relative minus A to the left. So that will be minus mass of m times A relative minus A. The negative sign is because I'm writing down the net force in the positive direction, which is taken to be the rightward direction. And what is the acceleration of B in the ground frame? So acceleration of B is the resultant of this A relative and A. And this angle is 60 degrees. So the horizontal component would be A relative cos 60 plus A. So I'll have plus mass of B, which is 2m, times A relative cos 60 is A relative by 2 plus A. So basically I've written down the net force on the entire system by writing down m1a1 plus m2a2 plus m3a3 in the horizontal direction for individual objects. So now I can solve this equation to get a relation between A and A relative, but if you, in this particular question, if you do it, you will get A as 0. So straight away you get the acceleration of the wedge C as 0. This is because of the particular values of masses given in the question. Suppose you had a different mass. Suppose like you had, let's say this block was 3m. In that case, you would have had a 3m here, and you wouldn't have gotten A as 0. You would have gotten some relation between A and A relative. And then you can write the force equation on the blocks in the frame of the wedge to solve for A relative. Now let's come to the case of a massive rope. So massive rope, massive in physics means it has some mass, non-zero mass. Suppose I have a rope hanging from a ceiling. So a very common problem is to find the tension at a distance x from the bottom.
Tension will simply have to balance the weight of the shaded portion. So if let's say lambda is the mass per unit length,
then tension will simply be equal to lambda into x into g. That will be tension as a function of x if lambda is a constant. So this rope is a uniform mass distribution. So this expression is actually very useful because we'll encounter it again in waves and again in properties of matter as well. Suppose I have a massive rope that is suspended from 2 points. So the equation that can be written for this rope and the equations that are usually used, let's say A and B are 2 points. So the equation that can be written is, let's say the tension is TA and TB at points A and B. This is the x-axis and this is the y-axis. So I can write TAX is equal to TBX. The reason is because for the equilibrium of this blue section of the rope, there is no other horizontal force. There is only gravity and the tensions. So, and if let's say this angle is theta A with a horizontal and this angle is theta B, I can simply write TA cos theta A should be equal to TB cos theta B. So that is one equation that you will have. The other equation is in the y direction. I can simply write TA sin theta A minus TB sin theta B is the resultant vertical component of the tension forces, should balance out the weight of the rope, weight of the blue section of the rope. So that is another equation. And a very important but a little less known equation is the one relating tensions to the height difference between A and B. So if the height difference between A and B is, let's say, delta y, then I can write Ta minus Tb is lambda g delta y. I'm assuming uniform rope, lambda is mass per unit length. So this is a very useful relation for the tensions and the vertical height difference. Now, where did this third equation come from? If I look at the blue section, and if you look at any element, let's say angle is theta here, so I'll have a dmg sine theta force for the gravity component along the rope. So dm can be written as lambda dl, dl is the length, infinitesimal length. So when I add up all the gravity components along the rope, I'll basically have integral of dl sine theta. But you should be able to see that dl sine theta is nothing but dy, and therefore integral of lambda dl sine theta g will simply be lambda g delta y, because integral dl sine theta is nothing but integral dy, and integral dy is delta y. If I were to just imagine all the forces along this blue section, so I have tension Ta, tension Tb all along the blue section, and the gravity components. So what is the resultant of all the gravity components? Lambda g delta y, and therefore I can write Ta is equal to Tb plus lambda g delta y. Basically, I've written the first equation along the curved string. So that's how you get your third equation. So I hope you have understood how we wrote down all the three equations. Let's use it in a question. Let's go to the next slide. A uniform rope of length L is held motionless on a frictionless hemisphere of radius r with one end of the rope at the top of the hemisphere here. And the hemisphere is made immobile by gluing it on a horizontal surface. So the hemisphere is fixed. And find where on the rope maximum tension force is developed immediately after the rope is released. So once the rope is released, I want to find where is the tension force maximum on the rope. So let's see how we can do this question. So first of all, I have my rope, and let's say it's subtending an angle alpha at the center. Alpha will simply be the length of the rope divided by the radius. Now if you release it, the only forces along the tangent or along the rope are the gravity components, and we already saw how much the gravity components will be. The net force along the string or along the rope will be lambda g delta y. So my acceleration would be lambda g delta y divided by the total mass. So it's very straightforward, lambda g, and what is delta y? Delta y is nothing but this vertical difference. So that will simply be r into 1 minus cos alpha. And total mass would be lambda into L. G into 1 minus cos alpha divided by alpha. I have just substituted L by R as alpha. I'll substitute alpha back in the end. So this is my acceleration. Now that I have my acceleration, let's say I'm going to find the tension at some general angle theta. So let's say at some theta, at some point inside the rope, I'm going to find the tension. Let's say the tension is T. So the tension is going to produce an acceleration, and the gravity components are also going to produce an acceleration. So the gravity components will be lambda g delta y. Now delta y for this section would be r into 1 minus cos theta. So I'll have tension plus lambda g r into 1 minus cos theta. This is the net force along the arc of the section, of the red section, should be equal to ma. So mass is lambda into r theta is the length of this red section here, times acceleration. So acceleration we already found out was g by alpha into 1 minus cos alpha. So now it's very straightforward. I get tension in terms of theta. See, I'll get it as, let me take lambda g r as common. So I'll get it as theta by alpha into 1 minus cos alpha minus or cos theta plus r. So now it's very straightforward because all I have to do is find the maximum of tension T. These are the only two terms that are varying as a function of theta. So just get the maxima. dt by d theta is 0, and you can get sine theta as 1 minus cos alpha by alpha. So this will be the angle at which you will have maximum tension. You can of course substitute alpha as L by R. So I hope you understood how we use that short expression for the resultant of gravity components along the rope. Basically, we're writing all the equations along the curve, along the arc of the rope. Let's come to springs now. So a spring follows Hooke's law. If I pull this block by distance x, the spring will apply a force of kx. Similarly, if I compress it, the spring will again apply a force of kx in the opposite sense. So basically, a spring will always apply a force in order to try to restore its natural length. Now this K, which is called the spring constant, and the natural length of the spring have a relation. So natural length is the length where there is no extension or compression. There is no force in the spring. The spring force is 0. So for a given material, the spring constant is inversely proportional to the natural length. Let's say I have a spring of natural length L0, and let's say I cut it in the ratio of L0 by 4 and 3 L0 by 4. So I've cut it in the ratio of 1:3. So L0 had a spring constant of K. So L0 by 4, because it is inversely proportional, the L0 by 4 will have a spring constant of 4K. And similarly, 3 L0 by 4 will have a spring constant of 4K by 3. So I hope you understood this concept. Now suppose you have two springs in series. So series meaning they are having the same force because they are connected to each other. So the K equivalent, I can replace this by a single spring whose K equivalent or equivalent spring constant is given by. And if you have two springs in parallel, so two springs in parallel means they have the same extension. So they can have different forces because of the different spring constants, but their K equivalent is simply K1 plus K2. So there's a very nice shortcut to calculate K equivalent for multiple pulley and springs involved. So suppose I have this sort of a situation. And this will honestly be very useful when we study SHM. That's where this shortcut method has a great role to play. But for now, we'll just quickly look at what it is. Basically, I can replace this entire system of springs by a single K equivalent, which will produce the same force on the block for the same displacement as the original system. Let's figure out what this K equivalent is. So what we need to first do is make sure that the tension on the block is T. The net tension on the block is T. So this will be T by 2 and this will be T by 4. And now the formula for K equivalent goes as 1 by K equivalent is summation of coefficient of T the whole square divided by Ki. So Ki is the ith spring constant, and coefficient of T, what does that mean? So for this first spring, K1, what is the coefficient of T? The tension is T by 4, so coefficient of T is 1 by 4 here. So this will be 1 by 4 the whole square divided by K1 plus for the second spring, what is the tension? T by 2. So what's the coefficient of T? Half. So 1 by 2 the whole square divided by K2. So that's how you get K equivalent. So if you have multiple springs involved, this is a very easy way to do this. I've included a couple of problems in the Pathfinder homework for this lecture where you can practice and use this shortcut method. And of course, we will encounter this again in a greater role when we study SHM. Now, a very important property of the spring is that spring force does not change instantaneously. What that means is that spring force cannot change by a finite amount in 0 time. And the reason is that for the spring force to change, if it is connected to a block, if the spring force has to change, its length also has to change. If its length has to change, that means the block has to move. So how can the block move by a finite amount in 0 time? That will imply infinite velocity. So that is not possible. The only case where this does happen is if the spring itself is cut. If the spring itself is cut, then the tension becomes 0 in the spring, and that means spring instantaneously goes back. The spring instantaneously goes back to its natural length. So this is the only case where the spring can suddenly change its length. I've just written that down. Unless the spring is cut, only in that case the spring can suddenly go back to its natural length. So let's do a question based on this. I'll go to the next page. In the setup shown, the pulleys, the cords and the spring are ideal and the masses of the loads are indicated in the figure. So I have a block of mass capital M and 3 other blocks whose masses are shown. Initially the system is in equilibrium. What should be the range of capital M so that the acceleration of the load of mass 2m here becomes greater than acceleration of free fall, so greater than g, immediately after the cord is cut at point P. So at point P, if this string is cut, I need the acceleration of 2m to be greater than g. So first of all, because it is in equilibrium initially, let's calculate the spring force. The reason I'm going to do that is because the spring force is not going to suddenly change. So the spring force just before cutting and just after cutting is going to remain the same. So we need that spring force. So first let's calculate that. So I have the tension here as mg, and therefore the tension here would be capital Mg by 2. So if I draw the FPD of this block, we have a tension capital Mg by 2, gravity small mg, and a spring force. So the spring force would be equal to capital mg by 2 minus small mg. Okay, now this blue string is cut. So once that blue string is cut, the FPD of 2m, you'll have a tension T downwards and 2mg. So basically when the question says that the acceleration of this 2m has to be greater than g, that means this tension has to be non-zero, tension has to be greater than 0. So basically this tension has to be greater than 0. And can you see that the block 2m and this block m, these two are connected by a string, this green string. So therefore, the acceleration of 2m, the magnitude will be the same as acceleration of m. Now what is the FBD of m, the green block? You have a spring force acting in the upward direction. The reason the spring force is acting upwards because initially it had to balance the weight of this block as well as the downward tension. So of course the spring force on this lower block had to be acting upwards. The same spring force is acting, whose value we calculated here. And what else is acting? There is an mg force and a tension force. So can I calculate the acceleration? The spring force, which is capital mg by 2 minus small mg, minus the gravitation force minus t divided by m. Now the same acceleration is also of 2m. So acceleration of 2m would be 2mg plus t divided by 2m. So I'm just going to equate these two. So I'll have 2mg plus t divided by 2m should be equal to capital mg by 2 minus 2mg minus t divided by m. So the relation that I'll get is tension is equal to capital mg minus 6 small mg. But now this tension has to be greater than 0 as we saw. And therefore capital M has to be greater than 6m. And so my answer would be B here. So I hope you've understood this question and how to solve it. Let's look at friction now. So we talked about the normal force, and at the very beginning I talked about the fact that normal force is only one component of the net force by the surface. So component of the force parallel to the surface is what we call as friction. So if you have an external force acting on this block, the friction will try and oppose the motion. So friction can reach a maximum value. So this is what we call a static friction. A static friction can reach a maximum value of mu s n, where mu s is the coefficient of static friction, and n is of course the normal force. And once the block starts slipping, if there is slipping between the surfaces, then the friction will be kinetic, and its value will be mu k times n, where mu k is the coefficient of kinetic friction. So mu k is always less than or equal to mu s. If in the question they only give mu as the coefficient of friction, they just say coefficient of friction is, let's say, 0.4, then that 0.4 is a value for both kinetic as well as static. So the resultant of the normal force and the friction force, let's say R, so R is called the reaction force or the contact force. So if they ask you find the force by the surface on the block, don't just write the normal force or don't just write the friction, you have to take the resultant force of normal and friction. And this angle here, phi, the friction by normal, this is called the angle of friction. So it's the angle between the resultant and the normal. And when friction is at its maximum value, tan phi will be mu. This is called the angle of repose. This is tan inverse mu. Now one very important result is that if you want to displace a block, if you want to move a block which is at rest, and you want to find the minimum force required to do that, so I have coefficient of static friction as mu s, let's say mass as m, let's say normal force this way, and when the block is on the verge of slipping, the friction will be static, so mu s n. So phi is a variable, so I can apply my force at any angle and I want to find the minimum possible force. So I can just write F cos phi is equal to mu s n. This is the horizontal force equation, just overcoming the static friction, and the vertical force balance would be F sin phi plus n should be mg. So from these two equations, you will get the value of F cos phi plus mu s sin phi in the denominator. So you can see that the minimum force will be when the denominator is maximum. The maximum value would be root of 1 plus mu square. You can use calculus or you can use trigonometry. If I just write that as z is cos phi plus mu s sin phi. dz by d phi would be minus psi phi plus mu s cos phi should be 0, and therefore you will get mu s as tan phi. So the angle at which you need to pull the force is phi is equal to tan inverse mu s, and the value of the minimum force would be mu s mg divided by root of 1 plus mu s squared. So I would suggest that you remember this. Sometimes in question they'll tell you the block is being pulled by the minimum possible force, and they can combine it with other chapters like find the work done. And then you'll have to use this expression for the minimum force. Always make sure that you're not making the common mistake of subconsciously assuming that the force is horizontal. When they say find the minimum force to pull the block, don't assume the force is horizontal unless explicitly mentioned. Now let's do a question on friction. The three blocks A, B and C whose masses are 9 kg, 9 kg and 18 kg are shown and they are released from rest. The coefficient of friction between block A and the horizontal surface is 0.5 and the coefficient of friction between block B and the horizontal surface is 0.5. Okay, find the acceleration of block C after just after the release. So if you want, you can pause the video and give it a try. You'll have to figure out which block is moving, if the blocks are moving at all, or if both are moving, you'll have to figure that out. So give it a try and then you can take a look at my solution. Okay, so first thing, if this tension on block C is T, it will be the same tension on A as well, it's the same string. And on block B, you'll have 2T. So because block A and B have the same mass, if block B cannot move, if the force of 2T is not sufficient to move block B, then of course A will also not move because the force on A is lesser. The maximum friction force on A and B are the same because they have the same mass, same coefficient of friction. So if B does not move, A will also not move. So let's quickly check if this is possible. If both are not moving, then C will obviously not move by string constraint. So the tension on C will be equal to its weight. So that will be 180 newtons. So is 2T lesser than the maximum friction? What is the maximum friction at B? The maximum friction at A and B are equal to mu mg 0.5 into 90, 45 newtons. So obviously this is not the case because 2T is greater than 45. T itself is greater than 45. So of course this situation is not possible. So what are the other possible situations? Another possible situation is that B moves and A does not. And the last possible situation is that all three are moving. So first let's check this situation. So if B moves and A does not, I can write my constraint equation as B has a force of 2T, C has a force of T. Let's say acceleration of B is this way, acceleration of C is downward. So virtual work method, 2T times AB minus T times AC should be 0. So acceleration of C is twice of acceleration of B. Now acceleration of C, can I write it as, I have an mg downwards, so 180 Newton is downwards. So 180 minus T divided by 18 is the acceleration of C. What about the acceleration of B? So B has 2T to the right and friction of 45 Newtons to the left. Because B is moving, the friction will be kinetic, so mu n. So I'll have 2T minus 45 divided by the mass of B, which is 9. So let's calculate tension, which comes out to be 40 Newtons. So you can calculate that on your own. Now how do we check that this case is correct? We assume that B moves but A does not. So let us check if tension is lesser than the maximum friction on A. The maximum friction on A is 45 Newtons and the tension that we got is 40 Newton. So of course the force of tension on A is lesser than the maximum friction, which means that A does not move, and that confirms that this case our assumption was correct. So this is the situation, and the question is asking find the acceleration of C. The acceleration of C is nothing but this. So acceleration of C would be 180 minus 40 divided by 18, which will be 70 by 9 meter per second squared. So answer would be D. So I hope you understood how we checked the case. We were lucky enough that the very second case that we checked got correct. It is possible that you may have to go through all the three cases to get to the correct one. That just depends on your luck, which one you choose first. Okay, let's move on. Let's look at another question. There's a very nice question that has appeared. I think it's in the Krotov book and it's appeared in the Boston physics competition as well. So usually this is solved using 2 or 3 simultaneous equations, but here we'll see how to do it in a single equation. So let's just read the question. A rope rests on 2 platforms which are both inclined at an angle theta, and which you are free to pick. That means the theta is a variable here. The rope has uniform mass density and its coefficient of friction with the platform is 1. The system has left-right symmetry. what is the largest possible fraction of the rope that does not touch the platforms, and what angle theta allows us maximum value. So let's say that the length of this rope, the segment is x, that is touching the platform, similarly x here. So the largest possible fraction of rope that does not touch the platform. So if I can find out the smallest value of x, then I'll also get the largest value of the length of the rope that doesn't touch the platform. So my question reduces to finding out the smallest value of x. Alright, so the normal force here is going to balance out the normal component of gravity. So that will be, let's say lambda is the mass per unit length. So lambda x g cos theta is the component of gravity perpendicular to the incline. So that's my normal force. And because you're asking the largest possible fraction, we're going to assume that it's on the verge of slipping. So we can say that the friction here would be mu n, and mu is given to be 1, so the friction is also lambda xg cos theta. Similarly, lambda xg cos theta, and the friction also lambda xg cos theta. Alright, what other forces are acting on this entire rope? It's gravity, of course, lambda g L. Let's say L is the length of the rope. So what I'm going to do is I'm going to avoid any internal tension in the string or in the rope, because that will lead to more variables and more equations. So instead I'm going to write the net force in the vertical direction on the entire rope. So these are my 5 forces acting. So in the vertical direction, this angle is theta, so this angle is also theta. So in the vertical direction, vertical downward direction, you have gravity lambda gl. In the upward direction, I have the vertical component of the normal force, which will be lambda gx cos theta multiplied by cos theta, so cos squared theta, plus the vertical component of friction lambda xt cos theta sin theta. And of course same thing on the right hand side, so just multiply this by 2. So that's how you will get x as a function of theta. It's very straightforward, no simultaneous equations needed. So x will come out to be L divided by twice of cos squared theta plus cos theta sin theta. And you can actually write this as, because you have 2 cos squared theta and 2 cos theta sin theta, 2 cos squared theta can be written as cos 2 theta plus 1, and cos theta sin theta multiplied by 2 can be written as sin 2 theta. So cos 2 theta plus sin 2 theta plus 1. Now it's pretty easy, because the maximum value of cos 2 theta plus sin 2 theta will ensure the minimum value of x. So the minimum value of x, what will be the maximum value of cos 2 theta plus sin 2 theta? You know that from trigonometry, it will be root 2. So L divided by root 2 plus 1. So minimum value of x is L divided by root 2 plus 1. What do I need? I need a fraction of the rope that is not touching. So the length of the rope that is not touching is L minus 2x, and the fraction will be divided by L. So 1 minus 2x by L, which will be equal to so this will be the fraction of the rope, the maximum possible fraction of the rope that is not touching, root 2 minus 1 over root 2 plus 1. And at what angle does it occur? That's also very straightforward. You can easily see that this value, cos 2 theta plus sin 2 theta, reaches its maximum value when 2 theta becomes 45 degrees. So 2 theta when it becomes 45 degrees, and therefore theta is pi by 8. So that's the angle at which you will have the maximum possible fraction of the rope that doesn't touch the platform. Now let's look at a case where you have a groove built in an inclined plane or in a surface. So suppose I take an inclined plane which is at an angle of theta, and let's say this is alpha. So this is a groove. So groove meaning that's like a slide or khadde ki tarah, in which a block can slide. So in physics, we assume that the width of the block is slightly lesser than the groove. This is something that we will always assume in our syllabus. That means it is in contact with either one of the two walls, either the right wall or the left wall of the groove. So the groove is, so I have a block here. So the block is in contact with the base of the groove, and then the groove has this red side, this is the side wall of the groove, and the back wall of the groove. So the block is in contact with either one of the two walls, the green wall or the red wall. Those are the two side walls of the groove, and it's in contact with the base, the blue shaded surface of the groove. So you can imagine that the block is in contact with two surfaces of the groove. So there will be two friction forces acting on the two surfaces of the block. So suppose I have coefficient of friction mu, and I want to find the acceleration. This block is released, and let's say mass is m. I want to find the acceleration. So first of all, what will be the component of gravity along the incline? So along the incline, we know the component of gravity will simply be mg sin theta, and perpendicular to the incline will be mg cos theta. Alright, now if I look at the top view, so I'm looking at the incline. So this is my incline, and this is my groove. And I have an mg sin theta force in this manner. Now there is a normal force in the outward direction towards us. That normal force will balance out mg cos theta. This is by the blue shaded figure in this diagram. The base of the groove is applying the normal force. However, mg sin theta, you see, mg sin theta has a component perpendicular to the groove. That component has to be balanced by some normal force. So that component will be balanced out by this red wall. So that will be a normal force by the side wall. So the normal force by the side wall will balance out the component of gravity. So this angle is alpha. The component of gravity perpendicular to the groove would be mg sin theta cos alpha. So the side wall of the groove will apply a force of mg sin theta cos alpha on the block. Alright, so now these two normal forces are acting on the two surfaces of the block, and corresponding to these two normal forces, we'll also have two frictional forces. So on the FPD of the block, mg sin theta, and the two friction forces, one along the base, which would be mu mg cos theta corresponding to this normal force, and one along the side, which would be mu mg sin theta cos alpha corresponding to this. Here we are of course assuming that the component of gravity along the groove is sufficient enough to cause slipping, so therefore we have kinetic friction acting. Alright, so the acceleration is along the groove. This angle will be 90 minus alpha, and therefore my acceleration would be, the component of gravity along the groove would be mg sin theta sin alpha minus the friction values. So let's say this is F1 and F2. So minus F1 plus F2, you can substitute that on your own divided by mass. So this will be our acceleration of the block along the groove. Now let's look at two block systems. So let's take the case where I have a force acting on the lower block. Let's say the force is a function of time. I have coefficient of friction mu1 and mu2 here. So the way to do this kind of question, where they can ask you find the time at which the slipping will occur between the two blocks. So force is equal to time means at 1 second the force is 1 Newton, at 2 seconds the force is 2 Newtons, and so on. So they can ask you at what time do the two blocks start slipping on each other. So always draw the FPD of the block on which the force is not acting, the external force is not acting, which is the upper block. So on the upper block, what is the maximum friction that can act? See, on M2, there's an external force trying to pull it to the right, so frictional force will act to the left. So therefore, by Newton's third law, the friction will act onto the right on the block M1. So I'll have mu M1G, mu1 M1G as a friction force. So this is the maximum possible friction force that can act on M1, and therefore its maximum value would be mu1G. And therefore, the system can move together as long as it's moving with an acceleration lesser than or equal to this. As soon as it reaches this acceleration, after that, M1 cannot go faster than that. M1 cannot have an acceleration greater than this value. So after this point, M2 will accelerate with a greater value compared to M1, which basically means that slipping is occurring. So when the system reaches acceleration of mu1g, till then I can treat it as a single body because they are moving together. The friction on the ground is mu2 times the normal force, which is m1 plus m2g. So can I write the external force minus mu2 times m1 plus m2g, this is the friction on the ground, should be equal to m1 plus m2 times acceleration, which is mu1g. And therefore, I'll get the force value as, so this is the minimum force to produce slipping between the blocks. So if you want, you can remember this as a formula as well, but I would suggest that you understand the process, because especially when the force is acting on the top block, or when you add in another block to make a 3-block system, you will need to go back to the process that we followed here. We can also plot the graph of acceleration versus time. So initially they were stationary until the external force overcomes the ground friction. So till the external force becomes equal to mu2 times m1 plus m2g, the acceleration for both were 0. Then they start accelerating, and they will accelerate together till what time? This time will be a F minimum. After which block M1 will acquire that constant acceleration. Block M2, however, will keep on accelerating which will be increasing in its value because of the increasing force. One thing to understand here is the slope will increase. If you compare the slope of the green line to the red line, the slope of the green line will increase because, see, when you write acceleration versus time, time is basically equal to force. So acceleration is force by mass. So mass is in the denominator. So mass here is in the denominator. You'll have some F2 for the friction on the ground as well, this value. But basically the slope would be 1 by m. And because the slope is 1 by m, the mass initially is m1 plus m2 in the red portion of the graph. But in the green portion of the graph, mass is only m2. So clearly the slope is decreasing because slope is inversely proportional to mass. Let's take a situation where the force is acting on the top block. Coefficient of friction is mu1, coefficient of friction is mu2. So once again, I want to find the time at which slipping will occur. So now this time I will look at the lower block. So on M2, see, on M1 the friction will act to the left, trying to oppose the external force. On M2, the top surface of M2, friction, the maximum possible friction will act to the right, and it will be opposed by the ground friction. So the maximum possible ground friction is mu2 times M1 plus M2 times G. So now if mu1 M1 G is lesser than mu2 times, in that case M2 will not move, because mu1 M1 G, which is trying to accelerate M2 rather to the right, that will not be able to overcome the ground friction. So in that case, it's very straightforward. A2 will simply be 0, and the upper block will start slipping when the external force overcomes the friction on the upper block surface, which is mu1 M1 G. So that is a trivial case. Let's look at the case where mu1 M1 G is greater than the ground friction, so M2 also is able to accelerate. In that case, M2 will accelerate. The maximum possible acceleration of M2 would be divided by M2, the net force by M2. Until then, till it reaches this maximum acceleration, the entire system is moving together. So can I write F minus mu2 times M1 plus M2 times G should be equal to this A max. So A max is when the slipping is just about to occur. So this is how you will get the minimum force to cause slipping. So you can calculate that on your own. There's no real formula that you need to establish or remember here. Most questions will involve numbers for the masses and coefficient of friction. So you should be able to follow the same process. And once again, in this situation, if I draw the graph, initially acceleration was 0 for both because friction has to overcome the ground friction. I'm talking about this case. Then they move together. Then M2 acquires a constant acceleration A max, and M1 will have an acceleration that will keep on increasing, and the slope will also be greater compared to this blue line for the same reason that we saw on the previous page. So let's do a question, but this time let me give you different values of static and kinetic friction. So let's say static friction is 0.4, let's say kinetic friction is 0.2. So this ground is smooth. Find the time when slipping occurs between the two blocks. And also try plotting acceleration versus time. So pause the video, try it out, and see if you got it correct. Okay, so the top block will have a friction here. So what is the maximum possible friction value? Mu s into n. So that will be 0.4 into 20. Take GS 10. That will be 8 Newton. So the maximum possible acceleration would be 4 meter per second squared. So till then they'll be moving together. A system of 5 kg, and the ground is smooth. So clearly F will be equal to 5 times 4, which is the acceleration. So at 20 seconds, the blocks are on the verge of slipping. We have to use the static friction here because on the verge of slipping means that the friction is at its maximum static value. Alright, now what is going to happen is just after t equal to 20 seconds. So I'm doing this calculation in order to plot the graph. Just after t equal to 20 seconds, there will be kinetic friction acting. So on 2 kg, there will be a kinetic friction acting. And how much will that kinetic friction be? 0.2 into 20. So the acceleration will suddenly become 2 meter per second squared for block 2. And for block 3, you had an external force of 20 newtons. And now instead of static friction, you'll have kinetic friction of 4 newtons. So now suddenly the acceleration will become 16 by 3 meter per second squared. So when I plot the graph, they're moving together initially and they will reach an acceleration of 4 meter per second squared. That's when the slipping will occur at 20 seconds. But just after 20 seconds, suddenly the acceleration of 2 kg will go from 4 to 2 meter per second squared. So this will be 2 kg. This acceleration will be 2 meter per second squared. And the acceleration of 3 kg will jump from 4 meter per second squared to 16 by 3. And of course, as we saw, it will increase with a greater slope. So this is how the graph will look like. So I hope you've understood how we calculated the time when slipping occurred and how we plotted this graph. Now let's come to the notorious 3-block systems which students usually struggle with, but it's actually just an extension of the 2-block systems and should be pretty straightforward if you've understood the previous 3 slides. So I'll start off with an example itself. So suppose I have, let's say 1 kg, 2 kg and 4 kg. Let's say force is acting on the bottommost block and let's say this coefficient of friction is 0.1, 0.2 and let me give you the ground as smooth. The question is asking find when slipping will occur between the 2 blocks and let's also plot the graph. So one thing that you need to figure out is there is a relation between these accelerations. Now the acceleration of C has to be the greatest because that is the block on which the force is acting, and acceleration of A has to be the smallest. A has to be lesser than equal to B, which has to be lesser than equal to C at all instants. The reason is because friction always opposes relative motion. If A starts moving faster than B, then friction is supporting relative motion, which is not possible. And you can just imagine it will be very absurd that you're pulling a 4 kg block and 1 kg is going faster than that. How is that possible? That is not possible. Alright, so the directions of friction, I'm pulling the block 4 kg. So I'll have a friction acting this way. So on 2 kg by Newton's third law, there will be a friction acting to the right and trying to accelerate it, which will be opposed by the friction on the top surface, which will further act on the right on the 1 kg block. So these will be the directions of friction. So what will be the maximum acceleration of 1 kg? So we'll start off with the topmost block. So the maximum acceleration of 1 kg, what is the maximum friction there? Mu mg. The friction there is 1 Newton. So maximum acceleration will be 1 meter per second squared. Now we have to check, can 1 kg slip on 2 kg? If 1 kg slips on 2 kg, that means there is kinetic friction acting on 2 kg. So there will be 1 Newton. And what is the maximum friction that can accelerate 2 kg to the right? That will be the friction between 2 and 4. So mu is 0.2 times the normal force is 30 newtons. So that will be 6 newtons. So the acceleration, maximum acceleration of 2 kg would be 2.5 meter per second squared. Now you check whether this is being satisfied or not. So maximum acceleration of 2 kg under condition that 1 kg slips on 2 kg is greater than 1 meter per second squared. So this condition is satisfied and therefore this assumption or what we are trying to check, if 1 kg can slip on 2 kg, that is indeed possible. If you got this acceleration here lesser than this acceleration, that means this situation or this condition is not possible. In that case, 1 and 2 kg will always move together and you can combine it and reduce your problem to a 2-block system. So in this particular question, the system is going to move together till they reach an acceleration of 1 meter per second squared. So when they do that, I can consider them as moving together of mass 7 kg. And when they acquire an acceleration of 1 meter per second squared, the force itself will be 7 Newton. So the time will be 7 seconds. So that's when slipping occurs between 1 kg and 2 kg. Now if I consider the other 2 blocks, after 7 seconds, 2 kg and 4 kg will be moving together till they reach an acceleration of 2.5. And you have a friction of 1 Newton that 1 kg is applying. I can just write F minus 1 is mass into acceleration. So F will be 16 Newton. So 16 Newton or 16 seconds in our case is when slipping occurs between 2 and 4 kg. So that's how you figure out the time instants when slipping occurs. It's quite straightforward if you follow the method. And if I want to plot the graph, let's do that on the next page. So initially the system is moving together till 7 seconds, after which the 1 kg block acquires constant acceleration of 1 meter per second squared. Then the system of 2 kg and 4 kg start moving, and from the previous 2 block system concept, you should now realize that the slope will increase. The slope will be greater than the red slope because the mass is reduced from 7 kg to 6 kg. So this blue graph will continue till 16 seconds, at which point 4 kg and 2 kg will have slipping between each other, and 2 kg will therefore now move with a constant acceleration of 2.5 meter per second squared. And after that, 4 kg will continue accelerating with an increasing rate. And also the slope of the green line will be greater than that of the blue line. So this is how you plot acceleration versus time. Now let's give you a question to practice on. Alright, now so the question is asking us, find when the respective slipping occurs between the blocks. So when the slipping occurs between 2 kg and 3 kg, and when slipping occurs between 3 kg and 6 kg, and plot the acceleration versus time. And the coefficient of frictions have been given to you, and the force is acting on the top block now is equal to time once again. So try it out, then you can take a look at a solution. Alright, now if I just label the blocks as A, B, C, acceleration of A now must be the greatest because that's the block on which the force is acting. So this should be the inequality. So first let's look at the directions of friction. So on 2 kg block, friction will be acting to the left in order to oppose this external force F. And then by Newton's third law, that the same friction will be acting to the right on the top surface of the 3 kg block. Now that be opposed by the friction on the bottom surface of the 3 kg block. And similarly, the friction will be acting on the top surface of 6 kg block to the right. So now let's calculate the maximum acceleration of 6 kg. Now what's the friction between the 3 kg block and 6 kg block? So mu is 0.2 multiplied by the normal force, which is 50 newtons. So that will be 10 newtons. So 10 newton will be trying to accelerate 6 kg. There's no friction on the ground. So acceleration will be 10 by 6, 5 by 3 meter per second squared. Now if 3 kg slips on 6 kg, we have to check if that is possible. So if 3 kg slips on 6 kg, what's the maximum acceleration of 3 kg? So what's the maximum friction on the top surface of 3 kg?
0.8 friction coefficient multiplied by 20 newtons. So that will be 16 newtons. And of course 10 Newton force will be acting on the lower surface of 3 kg. So the maximum possible acceleration of 3 kg block B is going to be 16 minus 10 divided by 3. This is going to be 2 meter per second squared.
So now you should see that this 2 meter per second squared is greater than 5 by 3. So the inequality is being satisfied. And therefore, the entire system is going to move together till it reaches an acceleration of 5 by 3 meter per second squared. And at that point, B will slip on C. So for B to slip on C, the entire system, which is of 11 kg, is going to be moving at 5 by 3 meter per second squared. So the external force is going to be the mass 11 kg multiplied by 5 by 3 meter per second squared, so that will be 55 by 3 newtons. So at 55 by 3 seconds, block B is going to slip on C. And as you continue increasing the force, block C is going to continue accelerating at this constant 5 by 3 meter per second squared, and block A and B are going to now move as a single system. So I can treat it as a block of mass 5 kg. So it will experience a 10 Newton force on the base, and the external force will accelerate it. So when this system reaches an acceleration of 2 meter per second squared, that is when slipping is going to occur between A and B. So F minus 10 is mass into acceleration. So F is 20 newtons. Therefore, at 20 seconds, slipping is going to occur between A and B. So let's plot the graph. So initially they're moving together, the entire system, till they reach an acceleration of 5 by 3 meter per second squared, which occurs at a time of 55 by 3 seconds. After which the block C is going to continue to move with a constant acceleration of 5 by 3 meter per second squared, and then block A and B will move together till 20 seconds, at which point the acceleration became 2 meter per second squared. Then the block B will continue to move with a constant acceleration of 2 meter per second squared, and block A's acceleration will continue increasing. And you should also be able to see that these slopes will increase as we go ahead with time, for the same reason that we've discussed in the previous examples. Now let's look at a very important concept, friction versus tension. So when you have both friction and tension acting on a block, let's see what happens. So suppose I have a block of, let's say, 2 kg and coefficient of friction is 0.5. Let's say I have an external force which is increasing with time t, and the block is connected to a string which is connected to the wall. So I want to find out how the tension varies with time. So in our questions, when the question says the string is inextensible, in reality it does have some negligible extension. Even though it's negligible, it's still non-zero, but that extension is actually responsible for the generation of tension. So till the string does not extend, tension will remain zero. So in the question, we are going to assume that the string is at taut length, but the tension is zero. What that means is that if you pull the string slightly, tension will be generated. It's at taut length, that means the tension is about to get generated, but the value of tension is still zero. So this is something that we're going to assume in the question, even though it may not be mentioned. So now for the tension to get generated, the string must get slightly extended, and in order for that to happen, the block must get slightly displaced. And for the block to get slightly displaced, the external force must be able to reach or overcome the maximum static friction. So first, till the maximum static friction is reached, tension will remain zero. So what's the friction value? The maximum possible static friction here is going to be 10 newtons, and therefore till 10 seconds, the tension is going to be zero, and the friction will simply balance out the external force. After 10 seconds, the friction is not sufficient to balance out the external force, so the block will get slightly displaced, the string will get slightly extended, and thus the tension will be generated. So t greater than 10, you can even put an equality sign. So at t greater than or equal to 10, I have the external force, I have the tension, and I have friction of 10 newtons. So the tension will simply be external force minus 10. So this is how tension will be generated in the string. So I hope you've understood what happens when friction and tension both act. Alright, let's do an example for you to practice on. So here I have two blocks of mass A and B, and I have an external force F pulling the block B. So this string is connected to a fixed clamp here, and also connected to block, the pulley is connected to block A. So both masses are 5 kg, both coefficient of frictions are 0.2. So let's say the tension in this red string is TA, and tension in this blue string is TB. So find out TA and TB as a function of time. So try it out and then you can take a look at my solution. Alright, first of all, the coefficient of friction is 0.2, so the maximum possible friction here would be 10 newtons and 10 newtons here as well. So first, once again, the external force has to overcome the 10 Newton force in order to produce any sort of tension. So T less than or equal to 10, both tension A and B are going to be 0. Now what happens at T greater than 10? The tension in TB, and you have the external force F here, and this will be 10 newtons of friction. So tension B will have to balance out the rest of the forces, so that will be equal to F minus 10, so T minus 10. But you have to understand that the force on block A is 2 TB to the right. So when 2 TB reaches the frictional force on A, only then will the tension in A be generated. Only then the tension in the red string will be generated. 2 TB is the external force for the block A. So the situation that we have here with F acting on B is the same situation we have here, but instead of F, we have 2 TB. So when will 2 TB reach the maximum possible friction of 10 newtons? So when 2 TB reaches, becomes equal to 10 newtons, that means the tension in B is 5 newtons. So when will that happen? We can see from this equation. So that will happen at 15 seconds. So for T between 10 and 15, the tension in A is going to remain 0. Tension in the red string is going to remain 0 because the external force 2 TB on block A has not reached the maximum possible friction on block A. And what about after 15 seconds? After 15 seconds, now I have 2 TB and I have the tension TA and I have friction 10 newtons. So TA will simply be 2 TB minus 10. What is TB? T minus 10 in terms of time. So this will be 2T minus 30. So that's how tension in A and B will be generated. So that's the end of this chapter. Solve the homework, solve the DPP and solve the Pathfinder questions that I've given you as homework. And I'll see you guys next time. See you at the top. Good night.